All right, I'm going to go over a couple of examples of Newton's method for you guys. I'm going to look at questions 3 and 4 here. See how to do questions 3 and 4. And we're going to approximate this to 6 decimal places. Now, what I want to remark here is you have two curves, the curve in purple set equal to that curve in black. Now, typically, the instructions for you would be to solve for x. And what that would do for you really is you are finding two points of intersection, because this is the location where they share the same, x and y coordinate values. So what you're saying is these two y values are equal. One is in purple, the other one is black, and we need the value of x such that this situation occurs where they do cross. So these are really points of intersection. Now, Newton method really helps us find roots of equations, or I should say roots of functions. So what you'd want to do is simply subtract both sides here from 2 cosine x. I'm going to subtract this term, and you now end up with x to the fourth minus 2 cosine x equals 0. Now, what that will do here is if we let f be now, this portion here, this is going to be our f. So we're going to call this f, we're going to let f be x to the fourth minus 2 cosine x. And since that equals 0, any solution is called a root. So this is why we say, or use the letter r, which means that solution, f of r, is 0. That means r is a root. So we're looking for a root. And they're saying to us to consider really the root in the interval from 0 to 2. So in this interval from 0 to 2 here, even though that's corresponding to the point of intersection, there's 2 points of intersection, but we're going to look at this solution in 0, 2. Now, you might say, what does it look like as a function f of x being x to the fourth minus 2 cosine x? And what I have here is essentially what this looks like. And as you guys can see, you're going to cross that x-axis for x to the fourth minus 2 cosine x. It's going to have a root at about 1.014. It's not 1, but 1.014. This is the location where you're going to cross the x-axis. Okay, that's what we're going to really look for. That's the root. Same thing over here. It has 2, but we're not going to find that root. We're only going to find the first root in the interval 0 to 2. And that's where we're going to start Newton's method. Okay, so back to Newton's method. So Newton's method is an iteration method. We're going to find the second value, because remember the first value, x1, is a guess. And we need f of x1 over f prime x1. So this is how we're going to start our Newton's method here. Okay, we went over the derivation in class. This is the starting point. That's my first guess. And then we need f of that gas, and we need f prime of that gas. So this is going to be Newton's method for this function here. So here's what I'm going to do. I'm going to go over to the scratch work here. I'm going to copy this information, and we're going to go over to, we got to remember Nope, it's the first one. That's the scratch work. Yeah, there we go. So I'm going to paste this information here. We're going to move this around. So we need the derivative now. So the derivative of f is 4x cubed minus 2. Now the derivative of cosine is minus sine. So minus the minus makes that a nice plus. So here's my derivative. 4x cubed plus 2 sine x. So we have the original function that we're going to use here in Newton's method. We have the derivative right here. We just need that initial guess. And what they gave us is right in here, they say, let that root value be, looking for the root in 0 to 2. So we're going to guess, I'm going to say, let's try 1.5. That's a nice value in 0 to 2. And that's where our root lives. So we're going to start with a guess of 1.5 here. So x1 will be 1.5. So I'm going to plug a 1.5 in here. Wherever there's an x1, that's our first iteration, our first guess. So x2 will be 1.5 minus f of 1.5 over f prime 1.5. So let's continue here and write this down. Our f function is x to the fourth minus 2 cosine x. So this will be 1.5 to the fourth minus 2 cosine of 1.5. The derivative is 4 times that 1.5 cubed plus 2 sine of 1.5. So here's the function. Here's the derivative. Here's our initial guess. And let's make sure that's a 1.5. So we're going to use our calculator, ladies and gentlemen, on this one to get the second value. We're going to use the calculator. And in the TI now, okay, what we really want to do is be careful when entering all this information here. So we're going to start with the fact that we have trig functions, and we better be in radian measure because the value of 1.5 is a real number. It's not a angle. So we are certainly in radian mode, and that's good. Okay, let's make sure we're in radian. So 1.5 is a real number. It's a radian value. Minus, I'll put parentheses for this numerator here. So we have 1.5 raised to the fourth power, come out of there, minus 2 cosine 1.5, close this, divided by another set of parentheses where we're going to say 4 times 1.5 raised to the third power, come out of the power position, the exponent. Now this is plus 2 sine of 1.5, and close this twice here. So double check. This is what we entered in the calculator here. So this will be x2 now. So we get the value here of x2. I'm going to write this down. This is kind of the work you want to show. You know, like on your test. We're going to write down those values here. Okay, that's x2 now. Okay, we're going to need x3. So x3 will be now x2 minus f of x2 over f prime of x2. And now we use here x2 as an input in Newton's method. Okay, so we went from 1.5 now to 1.1824. So what I recommend here, using this TI calculator, there's a special function key called answer. What answer is the prior answer. This is a very useful function in your calculator. It's very useful for Newton's method. So the prior answer will say here, hit second, and it's down here in blue. That's the answer key. It places the prior answer in its memory, and it calls it answer. So I can now really apply Newton's method without having to enter all of that information. So we just have to be careful now. Close that. It's prior answer divided by 4 times the prior answer now raised to the third power. Come out of there, plus 2 cosine of the prior answer. Close that again. So, you could go back and double check to make sure this is exactly what you're entering. Okay, because this is our functions. And we're going to get x3 now. So let's go back to the TI. And we'll hit enter. So x3 now is approximately what you see here. And I'm going to write down all this answer. 1.019955029. Okay, so this is x3. And notice that we haven't had very much duplication yet. So we're going to have to go for x4. And x4 will be x3 minus f of x3 over f prime of x3. We're now will use x3 being what we just got. And we'll get x4. But when we do that, we're going to use the prior answer function in the TI. Prior answer. So second answer minus parentheses. That's the answer raised to the fourth power. Come out of there. Minus 2 cosine of that answer. Close that. Divided by 4 times that answer raised to the third power. Come out of there. Plus 2. Remember, on the bottom it was sine. Sine prior answer. Close that twice. And now we start to get some duplication here. This is 1.013998385 here. Okay. So I write this down to show my work here. Now let's take a look at the duplication here. How many decimal points? After the decimal, 0, 0, 1, 1. So there's only two digits that are duplicated. They wanted this to the, I think it was 4 or 6, but don't recall. But we're going to keep going here. We're going to improve our accuracy. Looks like we're getting closer. Looks like we're going to converge to the root. And we're going to use the TI now. So remember, this will be x4 minus f of x4 divided by f prime of x4. We're going to approximate this here. Okay, so we're going to use the prior answer key. Second answer minus parentheses answer raised to the fourth power. Come out of there. Minus 2 cosine of that answer again. Let's close this. Divided by 4 answer. And that's not right. Raised to the third power. Come out of there. Plus 2 sine of that value called answer. And ladies and gentlemen, hit enter. And let's see what we get now. This is 1.013957616. So we write this down and let's double check now. We got 1, 2, same first two terms. There's 3 and there's 4. And this is now accurate to 4 decimal places. And we're on our way. Maybe x to the 6 or the 6th iteration will get us there. So the 6th iteration, we'll put equal here. This is what this iteration is. Will be the 5th iteration minus f of x to the 5th, f prime x to the 5th. So this would be the 6th iteration here. Okay, so we're already at 4 decimal places in terms of accuracy. We want 6, I guess. Okay. Carefully. Second answer minus parentheses, that answer, raised to the 4th power, come out of there, minus 2 cosine of answer, prior answer, close that parentheses, divided by 4, times that answer raised to the 3rd power, come out of the power position, you're now going to add 2 sine of that prior answer. Close that again here. And let's write this down. You're going to get 1.013957614. And if we go to the iPad now, let us see how many decimal places of accuracy that is now. What's the duplication? So far we got 0139 just like we did earlier. But we now have 5. And we now have 7. And in fact we have 6. And in fact we have 1. So ladies and gentlemen, that's more than 6. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8-digit accuracy. And I guess if they said to approximate to 6 digits, okay, our root then will be 1.0139. That's 4. 3957. We look at the digit to the right, it's a 6. So we add 1 to the 7, we make that an 8. And ladies and gentlemen, here's our root. This is the solution due to Newton's method. So if we look at Desmos, again, it looks like Desmos just simply was not as accurate as what we got. You know, if we scroll right in, maybe that'll increase our accuracy. Yeah, Desmos does not seem to be, you know, as accurate as what we got. And that's fine. But this is how we apply Newton's method. And we found a root. And let's go back here. There it is. This is the value they were looking for in the interval from 0 to 2. You know, this is the solution here, ladies and gentlemen. So this is how we apply Newton's method for, you know, 3. And it says, yes, 6 decimal places. Okay, we got even better. Now, I said I'll do a couple for you guys here. Now, what's nice about this question in number 4, that you don't have 2 curves set equal to each other finding a point of intersection. What's nice about question 4 is they gave you from the start right in here, okay, this is your function. It equals 0. So that function equals 0. So that means any solution there is in fact a root. You know, because you set that function equal to 0. That's the definition. A root is like an intercept. And we see a location there. Here's the curve now. they're telling us to find the root because it looks like there's two roots, right? There's 2 points of intersection in this picture. But they want us to find the one. Oh, I apologize. There's 3. So let's get rid of that. There's 3 roots here. Let me see. Oh, they want us to find the one right in here in this interval here. Okay. Between 2 and 3. That's what they're asking. To find that particular root of this, cubic function. So, and they want us to go again, I believe that was to, 6 decimal places here. So, okay, let me see if I can copy that function. All right, I'm going to try to copy this. And we're going to get to work. So this is number 4 here. Looks like it didn't let me copy it, so I'm going to have to write down the function. F of x. So f of x was 2x cubed minus 6x squared, 2x cubed minus 6x squared, plus 3x, plus 1, and I believe the interval is between 2 and 3. Okay, that's the location. 2x cubed minus 6x squared plus 3x. So let me double check. And it's between 2 and 3. Okay. All right. So we need a derivative, which would be 6x squared minus 12x plus 3, and we need a starting point, an initial guess. So I'm going to use x1 to be 2. This is my guess, ladies and gentlemen. We're going to start at 2. Because if we go back and look at this, we'll start at 2 because the root is certainly not at 2, but it's close to 2. And it's in the interval they told us. All right. Let's get to our scratch paper here. So we have all the important pieces of information. Let's write this down now. X2 will be that initial gas minus f of the initial gas over f prime of that initial gas here. And let's give this some color here, right? Here's my initial guess so you guys can see that. So that means x2 will be 2 plus f of 2 over f prime of 2. My f function now. F is going to be 2x cubed minus 6x squared plus 3 times 2 plus 1. The denominator, the derivative, is 6x squared, so it'll be 6 times 2 squared. And I think that's minus 12 times 2. Plus 3. So let's just double check here. 2x cubed minus 6x squared plus 3 times 2 plus 1. 6 times 2 squared minus 12 times 2 plus 3. So here's what we're using so you guys can see this by color. The derivative is green. And your initial seed again was 2 here. So we plug in the 2. The initial guess, 2, 2, 2, and 2. This kind of helps me to some degree, ladies and gentlemen. And, we're going to have to enter a pair of polynomials here in that TI, and that might be a little bit more tedious than the last example. So what I'm going to go and do here, so I'm not distracted by the information, I'm going to clear that out. We start with 2 minus, now put your parentheses here. 2 times 2 raised to the third power, come out of the power position, minus 6 times 2 raised to the second power, plus 3 times 2, plus that 1, close this, divided by 6 times 2 squared, minus 12 times 2, plus 3, and close that there. Okay, now you can go back and try to double check as you do this. We look to be okay. And so I'm going to write this down here, ladies and gentlemen. This is 2 point, a whole lot of 3's. It's not the same as 2, but just a whole lot of 3's. And I'm writing that down. And I'm now going to do the third iteration, which is x2 minus f of x2 over f prime x2. So my f function, my derivative, the seed, are the second iteration now. So we're going to do x3 here. Okay, we're going to find x3. But I'm going to use the prior answer function in the TI, which is gold here. So prior answer, it's going to be that 2.3333 forever. Minus in parentheses 2 times prior answer raised to the third power. Come out of there. Minus 6 times prior answer raised to the second power. You come out of there. Plus 3 times prior answer plus 1, and close this. All right. Divided by, I'm looking at, my scratch work here. 6 times prior answer raised to the second power. You come out of there. Minus 12 times second prior answer plus 3. Okay. And I'm going to just write this down here in the iPad because I'm going to try to compare digits here. We get 2.236714976. So the point I'm making here is so far after the decimal, we have no repetition. So we're going to need a fourth iteration. x3 minus f of x3 over f prime x3. We're going to need another iteration. We haven't seen duplication yet. Here's my function, derivative, my third iteration that's going to help me get the fourth iteration in Newton's method. So we're going to see what the fourth iteration will be. We're going to use prior answer. So second answer minus 2 times answer. We have to remember what that power was. That's the third power. So raised to the third power now. Come out of there. Minus 6 times that answer key raised to the second power. Come out of there. Plus 3 times that answer key plus 1. Close this. Divided by 6 times that answer key raised to the, remember 6 times what? Second power. So you may have to go back to your note, 6 times the second power. Right? And then minus 12 times the answer. Minus 12 times that answer plus 3. All right, close that now. So 6x squared minus 12x plus 3, that's the derivative. And we're starting to see the first iteration. 2.2249, not iteration. We're trying to see the digits that are repeating here. So now if we go back and compare, we say here's a 2, here's a 2. There's only one repeating digit so far. So we're going to have to go to that 5th iteration. So x to the 5th is x to the 4th minus f of x to the 4th over f prime x to the 4th. Okay, we're going to try the TI. Prior answer minus 2 times that answer raised to the 3rd power. Come out of there. Minus 6 times that answer key raised to the 2nd power. Come out of there. Plus 3 times that answer plus 1. You come out of there divided by the derivative now. That was 6. That answer raised to the 2nd power. And we have to remember, minus 12 times that answer. Minus 12 plus 3. Close this. And we're going to see some repetition. This is 2, 2, 4, 7, 4, 7, 4, 4, 9, 0, 7. So let's compare and see how much repetition do we have now here. So we got the 2, got a second 2, a 4, and a 4. So it looks like there's 3 digits accuracy. We're going to need to do this iteration again. So x to the 6th now, or x6. The 6th iteration. We'll try it again. Okay. We're going to use the TI. We're going to use the prior answer. And I think if you haven't been convinced to use that free trial version for the TI, this might be the tool that gets you there. 6. Our answer, I should say the exercise. Plus 3. Prior answer. Plus 1. Close that. Divided by, now the derivative. And the derivative was 6. Let's think about that. Derivative, look at our notes, is 6x squared minus 12x plus 3. So 6x squared minus 12x plus 3. And we're going to close that. And let's see what the digits are now. 2, 2, 4, 7, 4, 4, 8, 7, 1. We copy down those digits. And then now let's start to compare. 1, 2, 3. So 2, 2, 2, 2, 4 so far is duplicated here. So is 7. So is 4. And so is 4. And so we say that's 1, 2, 3, 4, 5, 6. We are at 6 digits. So this is accurate to within 6 digits. So we're ready to draw our conclusion. Our conclusion is that the root is approximately 2.224744. Now, when you look at the digit to the right from the last iteration, it's an 8. That means add 1. So your root is approximately 2.22474. Add 1, and you get a 5. And ladies and gentlemen, here you go. We have found the approximate root here to this, exercise. Now, let me go back and say, if we find Newton's method here, this is number 4, which is 2x cubed minus 6x squared plus 3x plus 1. If I go into Desmos here, I don't think I have it. But let's see if we can get it. Y equals 2x raised to the third power, 2x cubed, come out of there. I believe that was 6x squared. Oops. Come out of there. Minus 6x squared. We're going to have to plus 3x plus 1. Okay. Now, it looks like we may need to just fix this. It's a bit odd. We'll say from minus 5 to 5. Okay. Maybe that's a bit better. And I think I want to shrink the y values. Maybe that'll help us too. Minus 10 to 10. I don't know. Maybe that looks just a little bit better. Okay. Here's my point, ladies and gentlemen. We were looking for this solution here. This root here for that polynomial. Got to find that value there. So Desmos is not as accurate in their answer. They only went out to about 4 decimal places. This is 2.2247 in Desmos. 2.2247, and we went out to 2.2247. What we did was, 2.2247. We went out to a greater degree of accuracy. So Desmos only went out to 4 decimal place accuracy. The exercise was going out to a 6 decimal place accuracy. And these are some examples using Newton's method, ladies and gentlemen. So I hope you enjoyed, the demonstration as much as I did. I think Newton's method is a fantastic application of a derivative. It utilizes the linearization function and finding roots for the linearization function. And numerical methods are methods that are very much worthy of study because they actually solve more things than the traditional algebraic approach. Because there's more equations that we can't solve algebraically than the ones that we can. So there we go. I hope you guys have a great Veterans Day. And, you work hard on Veterans Day. You work hard on every day. And ladies and gentlemen, there you go.